Hi, my name is Clayman Gemelli, and I'm with the Esophageal Balloon Catheter Design Project, presenting here a Phase 2 design review for BME535 Medical Device Design Controls. And with me, I have my two team members.
I'm Sean Penn.
And I'm Daniel Sohatsky. First, we're going to talk about the project summary. Then, we're going to review all the action items for our last design review. Then, we will go over our deliverables as specified for this phase. Step 4 will be to review the quality plan for the responsibilities. Step 5 will be to review the design plan and the project plan. After that, we'll review the changes in scope and then review our DHF file. So our project is the esophageal balloon catheter. Whenever patients require mechanical ventilators to help them breathe, it's very important to know the intrapleural pressure inside of the lungs. This pressure is very difficult to get a hold of because you'd have to put a probe directly into the intrapleural space. Another method is to use the esophageal pressure, which is very closely related. Esophageal balloons are used to measure this pressure. The balloon is inflated to a specific volume, and then the catheter is hooked up to a respiratory machine. The balloon is inserted through the nostrils into the lower third of the esophagus. As the pleural pressure changes, the force is exerted onto the balloon. This force is transmitted up to the catheter and to the respirator, which then calculates the changes in pressure. There are currently no open action items from Phase 1 design review, as they were all completed. These first 4 deliverables were for week 3 of Phase 2. The rest of them were for this week, week 4. We will talk about all these deliverables further in depth later on in this presentation. With regards to the quality plan, in Phase 1, we were more focused on getting the functional requirements of the components within the minimized or acceptable range of errors. Also, we focused on the quality management and routine control in accordance with standard ISO 13485 from 2016. In Phase 2, we're more focused on the manufacturing process, assembly process, and potential hazard correlated to manufacturing, assembly, and operation. As a result, we flushed out all the components that did not pass evaluation or testing and modified and remanufactured them to provide better performance. We also determined that each batch of components should be retained with at least 5 individual samples for future quality inspection. In order to keep all of our deliverables in check, we decided to implement the Gantt chart. This chart lists all of our deliverables and all of the start and end dates that they're due. Extended to the right off the screen are the specific days that we have worked on the specific deadlines or that we will or are planning to. For weeks 1 and 2, we started with project selection, where we decided on our project for the semester. We sat down and we brainstormed several ideas on many aspects we could improve on esophageal balloon catheters. For each of these aspects, we drew up a few ideas or components as sort of rough ideas. For the brainstorm down selection, we took each one of these ideas or components and ranked them against each other in order to decide on the best ideas. From this, we were able to decide which components made it to the final design. The design input-output matrix was used to determine the requirements and desired capabilities of our final project and design, in addition to all the standards that we had to follow. And our project plan was this Gantt chart detailing on what days we would do the certain deliverables and when the deadlines were. For the second revision of the design plan, we added several aspects. First of all, we implemented a risk management or assessment aspect. We will talk about this more in depth later. We also added several design verification and validation strategies. In order to test how much force the balloon can withstand, we will use a constant burst pressure testing. In order to see if the balloon can last the entirety of the operation without failing, we'll utilize a fatigue test that puts the balloon through several cycles of stress. The balloon is attached to the catheter tube using an adhesive. We'll test the strength of this adhesive through a variety of tests also. In addition, we will be utilizing a tip loading weight test in order to measure how much weight the tip can withstand before fracturing. We will also utilize a variety of other mechanical properties to test the effectiveness of the catheter during operations. We will also implement manufacturing process validation and qualification strategies. These include defining the supply chain, material, and equipment requirements. We will also test method validations, component qualifications, and process validations. Compared to the first revision of the design plan, our scope has not changed at all. However, we did alter some of the manufacturers that we had to account for some of the manufacturers being unreliable.
Now I'm going to talk about the drawings, prototyping process, DFM, DFA, and the materials for our components. First of all is our balloon. Balloon slides onto an existing catheter tube and can be expanded upon an induction of gas. The widest portion is approximately 95 milliliter in length. And it is metric to distal side compared with the proximal side. As we researched into the manufacturing of the balloon, we found the two manufacturers, Kragner Medical and Northern Medical. They're all able to carry out the custom manufacturing with nylon balloon. The DFM process includes the following. First of all, extrusion of nylon catheter, then balloon molding to desired specifications. A cooling process is followed by quality inspection. The DFA process includes the unbag in styro field, wrapping balloon around the desired area of catheter tube, and finally glue the balloon to the shaft. We also want to carry out a preliminary testing and evaluation with constant burst pressure testing, cycle fatigue testing, and medical glue adhesion testing. Now I'm going to talk about the catheter tube, which is 5 French in outer diameter and approximately 86 cm in total length. The location of balloon is at approximately a third of the catheter length, away from the distal end. We have this kind of small hose, which is 0.75 milliliter in diameter to supply gas into the balloon. The catheter tube should be compatible to the balloon and the guide. The manufacturing process of the tube can be carried out by Optinova Group and Putnam Plastics, but the material must be polyamide. The DFM process includes injection molding and extrusion, heat cure, harvesting, shape adjustment, and quality control. The DFA process includes detailed assembly with the balloon and the tube, and connect with the port connector. Finally, a quality control will be carried out to make sure everything is fine. We also want to carry out testing and evaluation with mechanical property testing to the tube. So we have the specifications for the operation and a kinking testing to observe whether the tube passes or fails the kinking test during accelerated simulation of transportation. Our design also includes a Y-shaped port connector, which is to connect the catheter with the pressure meter and the syringe. It has 35-degree arm. The manufacturing process of the port can be carried out either by Stone Medical Devices or Merit Medical. The material can be either a combination of ABS and PP for the first manufacturer, or polycarbonate and PVC for the second. The DFM process includes injection molding, and the DFA process includes single injection molding and screwing a catheter tube onto the port connector. In the testing and evaluation process of the port, first of all, we want to test the mechanical properties. We also want to test the connection between the port and the catheter. Our design also includes a guide wire component, which is used to provide rigidity to the catheter tube and aid in balloon delivery. We found two manufacturers, Terumo Corporation and Boston Scientific. The DFM process of the guide wire include a grinding process with grinding wheel and control wheel, and the laser welding process. As for the DFA process, the wire is usually coated by PTFE or other substrates to enhance performance by reducing resistance and increasing rigidity. The preliminary testing and evaluation experiments mainly focus on the mechanical properties testing of the guide wire. Finally, I'm going to talk about the packaging and the sterilization process. The sterilization of our device should have transparent film in the front and a non-transparent card at the back. We found these two manufacturers, Burmese Company and the WePack Packaging Group. Both of these suppliers can provide packaging and sterilization service at the same time. The material included PETG, PEC, PC, PP, and HIPS. The DFM process of the packaging and the sterilization include a molding process to produce transparent tray. As for the DFA process, we want to place the device between the tray and the die card properly, followed by a proper ethylene oxide sterilization, and finally a sealing process to avoid further contamination. The preliminary testing and evaluation experiments include sterilization performance test, air tightness or leakage test, and a mechanical properties test. Here are some reminders. All components except guide wire require double bags, and no component require opaque packaging. The minimized shelf life of all components is 5 years, and for each component, 5 to 10 samples should be retained per batch. As for the supply chain, FMEA, we follow the grading criteria provided in this class to each component. As you can see, the majority of the component include a balloon, tube, and guide wire, has a risk acceptability of RA, which requires action. But as for the guide wire port connector and the packaging component, we have a supplier ranking of 2 and part criticality of low, so that does not require action. Now I'm going to talk about the design freeze for our esophageal balloon catheter design project. The technical specification and design intent are mainly listed according to our design requirements. The same design requirements were also listed in input and output matrix for our project. As for our tolerance analysis, the majority dimensions in this device include 3 decimal places, so we use the 0.13 milliliter for lots of dimensions. In this case, 0.13 milliliter is used as the default tolerance.
Alright, so next we'll be talking about the risk management plan. And our risk management is in compliance with ISO 14971. And in addition, our device is for the European market, so it is to meet requirements for the MDD, and it is a Class 2A device. The plan outlines our systematic approach to the risk management for our esophageal balloon catheter. I'm going to then now talk about some of the documents that go into this plan, or into the whole, risk management file. So we then looked at the ISO standard for Annex C and E. C was the intended use and safety characteristics. So this was helping us brainstorm and determine hazards applicable to the device. And then Annex E was the hazard ID checklist. So we went through the list of all the different types of hazards and listed out which ones our device fell under, or which hazards may fall under it. There were no energy hazards that we identified. The main harms were to the patient and normally from sheer mechanical forces with balloon bursting or shear forces of the catheter kind of rubbing or damage to the esophagus or nasal cavity. In addition, there was also a risk of contamination and patient infection as a result of that. So the hazard ID and risk analysis form, what we did here is taking our identified hazards, we investigated all of the identified risks and assessed the level of acceptability of these risks. So as you can see down here, this is our risk acceptability chart, and we have listed out the criteria for what makes it acceptable or not, with bar where it's broadly acceptable, as far as possible, and intolerable. We identified 21 risks overall, and we evaluated all of them. We had 17 that were BAR and 4 that were AFAP. So then after identifying our risks and ranking them, we then looked further into mitigating the risks. First, looking at the application at FMEA, there were 3 AFMEAs hazards that were identified as AFAP. As you can see here, this is the list of kind of all the application hazards. Some of them being because of inadequate training, a lot of times user error, carelessness, contamination, things like that. And so actually going back here, if you see the 3, hazard 2, 3, and 21 are AFAP, and these are damage to the patient, either infection or to the nasal cavity or esophagus. And so to help mitigate that, some of these are a lot of proper instructions, making sure the users know how to position the catheter if it gets stuck, where you don't just keep pushing it in to, you'd injure the patient. Possible improvements to the tip for the catheter to help minimize damage, making it more flexible. This also helps provide more tactile feedback. Hazard 3, better training of ways to position the patient, because if they're oriented in the wrong way, it's harder to get the catheter in. So helping teach that, as well as better warning labels, clearly stating this is single use only, don't reuse this catheter. So for the 3 that were identified as far as possible, as talked about in the lectures, we kind of assume that they stayed at this AFAP level for this next page, looking at really the risk-benefit analysis and trying to mitigate it. So what we looked at here is with the risk-benefit, the first 2 especially, hazard 2 and 3, we were not able to bring it below AFAP. However, we really believe the benefits outweigh the risk, as this device is really necessary for calibration of mechanical ventilators, which could then, improperly calibrated, could really cause harm to the patient. So we think the benefits definitely outweigh the risks. Hazard 21, I think, can be brought down to broadly acceptable, because, with clear labeling, it should be very rare that a user would try to use this catheter again on a different patient or even on the same patient. Next is the design FMEA. One of them was identified as far as possible. This is hazard 10, and this is due to improper orientation or operation of it. If they're not paying attention, they may overfill the balloon, maybe causing it to burst, which would then be could cause a lot of harm to the patient, although would be pretty rare. Designing the balloon to meet safety standards and prevent it bursting is very critical for this. Also requiring an additional personnel would help making sure the user doesn't make kind of stupid errors if they weren't distracted and they weren't watching about how much volume they're filling the balloons up. There were no process FMEAs identified requiring further risk reduction. As you can see here are the 2 PFMEAs listed. All right, next, so after going through this whole risk management, we then generate a risk management report. As you can see, there's 3 main hazards that were, not being able to reduce below as far as possible, but we really think the benefits outweigh the risks here. In addition, this report compiles all this information. It also talks about post-production risk reporting. So once the device is out in the field, we want to make sure we're gathering any hazards that are found on the field and bringing them back and going through the same risk reduction and risk analysis. Design history file. All the documents that we've been working on in this class all have been revision controlled and have a DHF folder created. So all of them are being in their proper places for the file. And this is consistently being updated. Some of the files from phase 1 have received revisions, and that has been noted. And then finally, current actions for this phase 2 design review. For the class, some of the action items are to watch presentations from the other teams, taking minute notes, and posting any follow-up questions, as well as answering questions from our own presentation by the other two groups. And so that is really our main action items for this design 2 phase review. We didn't identify anything specific with this, risk analysis or anything that really needed some follow-up action items. All right, thank you so much. I hope you enjoyed this presentation.